I'm teaching a reservoir sediment modeling class next week with the Corps' reservoir sediment specialists, John Shelley and Paul Boyd. And we developed a workshop that's a simplified reservoir model with local data. And so I was about to sit down and do a dry run of the workshop just to make sure everything works. And I thought, hey, why don't I turn on the camera and capture this, both for the students in the class, but potentially for anyone else, because even though it's a simplified model and not really ready for production work, it does illustrate a number of the best practices and like assumptions you need to make, and maybe not so best practices that you would encounter in a reservoir sediment model. So what I'm going to do is, just as I kind of do my dry run of this workshop, I'm going to turn on the camera. This will be a longer video because I'm going to go all the way through a model, starting with the geometry and ending with a run. And so we will hit all of the major steps of building a simple reservoir sedimentation model. And so here is my domain. I've got a relatively truncated geometry that's built off of a contour shapefile, so it's not the highest quality, but it's good enough for what we're doing. And then we also have about 25 years of flow data and reservoir stage data. And so you can go look at some of the other videos where we talk about different ways of modeling a reservoir, but we're just going to do the simplest approach here. We've put our downstream cross-section on the upstream side of the dam, which means that if we use that as a downstream stage boundary condition, then we will operate the dam essentially historically. I'm basically going to follow these steps. I'm going to add the quasi and steady flow data. I'm going to add the sediment initial conditions. I'm going to add the sediment boundary conditions. And then in the piece that I think is probably going to be most valuable, I'm going to walk through the options menu in the sediment data and choose the options that I think are best for a cohesive reservoir sediment model. And then we'll run the model and look at some results. And I'll put time markers in the comments below. So the first thing we're going to do is add the quasi and steady flow data. And of course, you can do this as an unsteady model, but quasi and steady is a lot more stable, and we're building a initial simplified model, so we're going to do it as quasi and steady. So you'll either go to Edit, Quasi and Steady Flow, or you'll press the Quasi and Steady Flow button, and you'll get this editor. And you'll notice that the editor automatically populates the upstream and the downstream boundary condition. And when you click on these, only the boundary conditions that are appropriate for that show up. So let's start with the upstream boundary condition. We have 25 years of data in CMS. And you'll notice that that's about 9,670 flows. So we will click the flow series because that's the only one that's available. And the first thing we want to do is fix the start time. These data have an actual start time. We know it. It's the 1st of January in 1997. So I'm going to go switch to fixed start time and put in 01 January 1997. If I do this, that means that I don't actually have to start at time step 1. I could actually run 2 years in the middle of this if I wanted to run a flushing model on a high flow or something like that. And so I'm going to fix this start time. And then what you'll notice is we actually only have 100 rows by default in here. And so you have to go and change the number of ordinates. And so we're going to call this 9670 so that we have enough rows for all of our flows. And then I'll just come in here and get my flows. Excel trick, Control-Shift down, and it'll get everything in that row. Control-C copies, and then you come up here, just click on the heading, Control-V, and that copies our flows in CMS. All right, so then we have these other two fields. RAS has these two time steps. The computational increment is actually the time step. That's what the model is going to use to compute. The flow duration is just how long are each of these flows that you're putting in. If they were just daily flows, we could do it like the Unsteady flow editor, but they don't have to be regular. You could put in irregular intervals. In this case, they're regular. And you'll see that these are, in fact, daily flows, which is appropriate for a system of this size. And so what I'm going to do is, that means that they're coming in at a 24-hour time step. So I'll just put a 24 up there and a 24 down here. And I'll hit interpolate values. And now we have daily data. Then a little bit more sensitive is this computation increment. Now, the computation increment is generally the biggest problem with a lot of models I see. This is a reservoir model, so if you choose the correct options, a lot of times it won't be as sensitive, but in general, people run computation increments that are too large. The problem is you actually kind of want to run large computation increments when flows are small and there's not a lot of sediment load, and you really want to focus your runtime on when flows are large and you've got a lot of morphological movements. And so what you should do is kind of start with your best estimate and then make the time steps bigger and smaller. It's called a convergence analysis until you see that there's no change. I'm not going to do that. I'm going to make a first estimate, but before I delivered a model like this, I would do a convergence analysis in order to make sure that by changing the time step, I don't change the answers. And so I want to have these computation increments, or the computational time step, change with the flow. But I've got 9,000 of these. I don't want to go in and type them in. So I'm going to use this option down here, the compute computation increment based on flow. And it says, hey, this is going to wipe out all of your computation increments. That's okay. I don't have any. And so I'll say yes. And so now I can go in and put a range of flows. And so you want to start with 0. And then the other thing you want to look at is you want to make sure you complete the whole range. And here the max flow in CMS is about 500. And so we're going to kind of make sure that the range includes 500. So I'll come here and I'll say from 0 to say like 50 CMS, those are low flows. I'll go ahead and use my 24 hours. I probably wouldn't do that in a project. I probably would have a max of 6 or something like that. I'd go in and compute a current condition actually, but we'll just do that for the workshop. Then let's say up to 100, I'll drop it to 12. Again, that's higher than I'd probably start with, but we'll do that. And then up to 200, now we're going to get down to a 3-hour time step. Up to 400, we'll go to a 1-hour time step. And anything above 400, let's go to 1,000, because this model could be used for future extreme events, and so we want to make sure that we capture those. We'll make that 0.5 hours. Okay, so now you'll see that basically all of these have computation increments associated with them. And so if we press OK and then reopen it, now we can plot it, and you'll see that we have our hydrograph. This is a histograph, right? It's a quasi unsteady flow, so it doesn't look like a curve like you might be used to an unsteady flow. These are constant flows over the period of time. Okay, so that's our upstream boundary condition. Our downstream boundary condition is going to be the stage at this location, and we have the pool elevation, again, daily over that period of time. So I'm going to click on here. I'm going to go stage series. I'm going to do the same thing. I'm going to fix the start time, 01 January 1997. This is a step a lot of people miss, and I think a lot of models run into problems with that. Next, I'm going to set my number of ordinances. We are at 9670 again. Then I'm going to come back to my data, Control-Shift down, Control-C, and then Control-V to paste those data over here. And then again, these are coming in as daily data, and the downstream stages don't have computation time steps with them. If you had like a tributary flow coming in, that could have its own computational time step, and then the model would find kind of the least common denominator. But stages, we just put those in at whatever they were defined at, and then we sample those. So we'll just put 24 at the top and 24 at the bottom, interpolate those, hit OK, and we're good to go. All right, so we have quasi-unsteady flow data. Well, we have the flow data, but we actually aren't done. You see, I put this little required down here because people kept forgetting the set temperature data. And so you do need to set temperature data. So we're going to open that up. But what you're going to find is that I actually don't have any temperature data. And so my opening offer is, 15 degrees centigrade. We will improve this model as more data come to the table, but for now I just need some sort of like reasonable constant temperature. I think the next thing I'll do, talking to the local experts, is, yeah, but what's the range? So we could kind of put the low in the month that it is and the high in the month that it is, and then create like a cycle, something like that. That's something I do pretty often, but for now I have no information. So I'm just going to start with 15 degrees centigrade. And a good way to put in a constant is just to put in a big number. I like to put in 240,000 because actually there's a limit to how big this number can be, but that's divisible by 24, and it's a pretty big number, so I'll put that at the top and then put it again in the bottom, interpolate. And so now basically we've got this huge time step of just 15 degrees centigrade. You could just leave that at simulation time, but I always like to fix the time even if it's synthetic data, so I'm going to make that 01 January 1997. Okay, so now we have our quasi and steady flow data. I should have saved this already, but we'll save it now. And we'll just call this 1997 to 2022. All right, we have our flow data. So the next thing we're going to do is enter our sediment data. So to enter your sediment data, you'll go Edit, Sediment Data, or you just press the Sediment button here, and you get your sediment data editor. Okay, so the first thing, you'll notice there's a bunch of tabs up here. We only really care about two of them. We care about the initial conditions and boundary conditions. We're not doing any bank failure analysis, so we'll just leave that. And so we'll start with our initial conditions. Well, the first thing we need to do is define our control volumes. And the control volumes are your movable bed limits. You know, what part of your model can erode or deposit, but specifically erode, and then how deep can erode. And that's kind of the reservoir of sediment that's available to be eroded. Now, we're doing a reservoir deposition model. And so there's a little trick here because deposition is actually a lot easier than erosion. And one of the hardest parts is to get the upstream reach of your reservoir stable and not to erode below where it actually erodes. And so if you're really just looking at a depositional model, or if you're looking at a flushing model where you would only erode what has been deposited, one thing you can do to simplify your modeling a lot is just say, well, with my initial bed, at the closing of the reservoir, because I'm modeling this reservoir from close to present, we're just going to say my control volume is zero. Zero depth. I have no sediment, which means that whatever that initial bed is, that's like a flume. It's not going to erode below that. You will be able to deposit sediment on top of it and then erode that sediment, but it's not going to erode into the materials beneath. And since I actually don't know what the materials are beneath, it would take me a lot of time to choose a artificial gradation that would make those stable. And so this is actually really helpful simplification for models like this. You could also go in and define those elevations if you wanted, but this is just as easy. So now what I'm going to do is if I hover over the bottom right corner of that, I get a plus, and that means that I can drag. So I'm just going to drag that to every cross section. So now every cross section has a zero maximum depth, which means that we're going to be able to deposit and then erode the deposition, but we aren't going to erode into whatever's beneath that. And that'll simplify a lot of things, as you'll see. Then the next thing we need to know is what are the left and right limits of this control volume, or our movable bed limits. Now you might think, well, we don't have a control volume, it's zero thickness, so why does this matter? Well, this matters for a lot of other things. A lot of times we multiply the transport functions. The width that we multiply those by is the distance between these movable bed limits, and we also only allow erosion or deposition within these movable bed limits unless you make a different decision, which we will. But for now, the movable bed limits end up being pretty important. But because later on I'll show you that we're actually going to deposit outside of the movable bed limits and limit erosion inside the movable bed limits, then setting the movable bed limits to the channel, especially in a reservoir setting where you're only going to erode deposited material, isn't a bad estimate. And so we have this button right here. You don't always use this button, but in this case, use the banks for the movable bed limits, goes in, and these were red dots because the red dots were the banks, but we're putting the yellow dots over top of them to show, hey, these movable bed limits are actually on top of your banks. Now, if you wanted to say move those, we have these buttons up here, and so you can see if I move the left movable bed limit over to, now we've got a different movable bed limit and bank station. But for now, we're just going to use the bank stations as movable bed limits. Then we need bed gradations at each of these cross sections. And that's a big lift because no one hardly ever has bed gradations at every cross section unless you're on the Missouri. And we actually have very few bed gradation measurements. And the bed gradation measurements we have are not particularly useful for this because they're measurements of the deposited sediment in 2022. And so it's not reflective of what was in the bed back when the reservoir closed back in 1997. So we're going to need to make it up. But here's the thing. It's not going to be a sensitive parameter because we're not going to be able to erode into this material because we set this as a zero. And even if we were to set this as an erodible bed, then it would only matter in the upstream portion. In the downstream portion where you have the reservoir pool, you're never going to erode anyway, and so it would just deposit on top of it. And so this doesn't really matter. but you need it. So I'm going to go in and I'm going to call this synthetic bed gradation, just so I know, just so that I and future users know I made this up. And then basically I'm going to say it's 10% wash load. So I'll want my 10% to be, at the fine sand, and we'll kind of distribute this pretty randomly. And then I'll probably want everything to be smaller than coarse gravel. And of course, I could actually compress this more to save runtime, but the runtimes are pretty short, so I won't worry about it too much. And then usually there's kind of a jump around here, so I'll make this 30 and I'll make this 70, 20. Something like that. Again, doesn't really matter because it's not sensitive, this parameter. Okay, so then I'll go in and I'll just select that here. And then if I hover over this and pull this down, then that populates. Now, this is the only kind of model where that doesn't matter. Most other models, this is one of the most sensitive parameters. So I don't want you to get from this video, hey, that doesn't matter, you can make it up. But because we're doing a reservoir model, which is mostly deposition, but we're only allowing it to erode the sediment deposits, it's only that case where this is not a sensitive parameter. Okay, so we've defined our initial conditions. Up here, we're going to select a transport function. Now, we're going to have almost entirely cohesive sediment coming into this, so the transport function also is not going to be very sensitive. Again, one of the only cases is where that's true, but I'm going to choose Larson-Copeland because Larson-Copeland does extend down into the silt range, so that if this transport function was to be invoked, it would be at least the most appropriate one. We're going to leave it for the defaults for sorting method and the fall velocity method. Okay, so those are your initial conditions. Let's move on to your boundary conditions. When I save it, save sediment data. All right, so next, I need to define the sediment flux upstream. And so there actually are some sediment measurements at this upstream boundary condition. It's complicated because it's not the whole watershed, but because it's a flow load relationship, we're going to apply it to the flows from the whole watershed. And I think that it's going to be pretty appropriate. And so we're going to define a rating curve here, but let's actually look at how I developed that rating curve because I use tools in RAS to do that. And so what we're going to do is we're actually going to close out of this. And what you'll see here is these are the data I was provided. I have dates of flow load pairs. And you'll see that I actually have about 600 measurements of flow load between 2001 and 2020. That's not bad. And so what I'm going to do is I'm going to open the tool that we've developed in RAS to do this. And so if you go to the HD editor, the hydraulic design editor, so you can go run hydraulic design function, or you can press the HD editor. And that'll bring up the bridge scour analysis tool, which is not what we need. But if you go to type and you go to rating curve calculator, it'll open up the tool that we use to develop the statistics to develop a flow load rating curve from these data. So we have a lot of videos on this tool. If you are interested in how to use this tool, we have extensive videos on that, but we're just going to kind of run through it quickly. Generally, this tool is set up to download data from the USGS data site. But this reservoir is not in the United States, and so the data aren't available just from the USGS portal, but we have them right here. And so what we're going to do is we're just going to import the data, and to do that, all you have to do is have your data in this format. One column is date, one column is time, one column is flow, and one column is load or concentration. Now, we don't have time. Is that okay? That's totally fine. In fact, if you don't have date or time, you can just leave those two blank as well, but you do need all four columns. And so in this case, having a date without a time is fine. We're just going to assume that it kind of happens on noon of each day. And so what I'm going to do is I'm just going to go Control-C, copy all these data, and then I'll come over here into the rating curve calculator and go File, Import, and then we'll go all the way down to the bottom from Clipboard. And it says, hey, are these loads or concentrations? Now, because this is an SI, we have to kind of keep we kind of have to do this right, because in 6.4.1, the SI conversions aren't great. You have to bring it in SI and kind of keep it there. We'll have that fixed for 6.5. But we're going to say, yeah, it's loads, import, and we import the data. And you can see that it imports all these flow load relationships and then starts as a kind of an opening offer, fits a power function through them with the bias correction functions. All log transformed power function fits are fundamentally and systematically biased, and so you have to unbias them with either a Dwan or Ferguson correction factor. I have videos on that if you want more information on that, but that's what we've done. Okay, so we could just run with this, and in one of the simulations we do. But we want to look at some other things too, like you can look at stationarity, and these data are actually pretty stationary. They don't change significantly with time. You can look at hysteresis and look how the kind of rising limb and falling limb of the annual hydrograph changes. But what I'm interested in is the question, does one single line fit these data well? And so we've added this LOS, this local regression, to kind of evaluate that. And I'm going to change the span to 0.5, which just means that for each of the local regressions, it's going to use about half the data to look at what if we just fit a regression to this part of the curve. And so then if you go in and you calculate the LOS, you'll see that it fits a curve, and this is not bias corrected, and so it plots lower, but it's the shape that we care about. It fits a curve that's relatively pretty straight locally through here, but then really tails off at the end, which suggests that maybe we're going to overcorrect on the high end. Well, we have a fix for that. And what we could do is we could fit a piecewise linear model to that. And so I'll go in here and say, hey, go ahead and fit a piecewise linear model. And so what it'll do is it'll actually fit two curves to minimize the residual of the regression. And what you see is actually it finds the statistical minimum, the inflection point with the minimum residual and a lower residual than this straight line is around 125 CMS, which is about where we see the low S turning over. And so I actually like this piecewise linear fit. Obviously I wish I had more data on the upper end of this curve, but our reservoir models is going to be more sensitive to this 50 to 500 CFS range. And so we want to make sure that we're kind of getting that as close as possible. So what we'll do is we'll come over here to the result. You see it gives us the coefficients here, but we actually want to just type this right into RAS. And so I'm going to go 0.01 as kind of my low bound. And then I want to put in the actual inflection point because I want to get a load for that as well. And then again, I'm going to kind of look for a high end. So I'll just say 1000 CFS. And what we get here is now we have the loads associated with this piecewise linear regression with the bias correction that we can put right in the model. So now I'm going to go back and open up my sediment data, and I'm going to open up the boundary condition and the rating curve. And now I want, how many sets do I want? Well, in general, you want as few sets as possible because you're going to be adjusting this in the calibration process. So if I can get away with 2, I do. But in this case, I need to capture the inflection point. So I'm going to need 3 sets. And so now my flows are 0.01. I'm just going to kind of transpose these data in here, 125 and 1000. And what loads do those go with? Well, again, about 0.1. It's totally appropriate to round these because these numbers are, kind of estimates anyway. And so those are our data. That's our flow load relationship. And if we open it up and we plot this, you'll see we have a piecewise linear curve that looks like this. Okay, so we have our loads. So what's all the rest of this white space here? Well, RAS, like most sediment transport models, is a grain class specific model. And so it's not enough just to tell us how much sediment is coming into the model. We need to know how much sediment is coming in each grain class. Now, unfortunately, in this model, like many models that we work on, we don't have any of this data. We only have the loads. We don't have any idea how those loads are broken down into different gradations. But I've already shown you the data we have, which is kind of the interpretive key to this. If we go back to the bed gradations weren't useful for initializing the bed, but these bed gradations, these are taken after a couple of decades of deposition. So this material that has deposited in the reservoir is actually characteristic of the flux that's coming in the reservoir that you want to model. And so if we look at this, there isn't a lot of spatial variation that's predictable. And so if you kind of look at the overall averages, we're looking at about 60% clay, about 30% silt, and about 10% sand. And so that would be a pretty good opening offer. And so we could start with that. If we just said, okay, 60% clay, and then we want 30% silt, but we need to, split that up over 4 silt grain classes, because what you don't want to do is you don't want to just go 60, 30, 8, because it's a reservoir model. So it's going to try to, you're going to get much more even deposition if you spread that out. And so then we'll go ahead and put 8 there. So that would be kind of the best use of the data. But run this model a couple times, I know how it behaves, and I also know how sediment models behave. And generally, you want to reduce clay. A couple of reasons for that. One is that when the clay is measured, basically it's deaggregated. And so when you're actually measuring the gradation of the clay, you're measuring the individual clay particles. But when clay is you're actually measuring the individual clay particles. But when clay is transporting, it's often transporting in flocks or clods, or even with silt too. So in general, these gradations are going to be coarser. The finer end of these gradations are going to run coarser in your depositional model than in your actual samples. And so kind of as an opening offer, I'm going to just drop that to 50. I might drop that to 40 or 30 eventually to get it to run. And in general, too, these are the materials that aren't going to fully deposit. And so depending on what your trap efficiency should be, you might need to reduce this number more. Is that fake? No, it's not, because a lot of clay is transported in silt-sized grain classes. And actually, a lot of silts are transported in sand-sized grain classes because they aggregate with the clay. And so then I also know that in general, a large sand content is going to over-predict the amount of deposition upstream because of the low energy up there. And I tend to think that a lot of times these samples collect ambient material. And so I'm actually going to just wipe out the sand for now and just run 50% clay, and we'll just say 20, 10, 10. Now, we have the opportunity to make that change with flow. As flow increases, does this get coarser or finer? Well, that's a big question that I've asked in publications, and if you're interested, I'll put a link below. But we actually just made this up. So do we actually have any information about how this changes? We don't. We could coarsen it, but in general, you don't want to make your input more specific than your information. Now, again, I just kind of made that up. How comfortable are we with that? It doesn't totally matter, because this is our least certain data. This is the data we have kind of least information about, which means that when we go to evaluate and calibrate the model, these are going to be the first ones changed. So we're going to put our best guess in there to run the model, but then we will revisit these data. So we have finished our sediment initial conditions and our sediment boundary conditions. But we're not actually done with our sediment data. And this is the real reason I wanted to run this video, because a lot of you have kind of seen me work through these online before. But the main things I wanted to show you were the options that you should use for a reservoir model, because if you don't use some of these options, you're going to get a terrible result. So we're going to go to options, and we're just going to start here with user-defined grain class. We'll just kind of work our way down through. And so in these, most people probably have never changed their user-defined grain classes, and that's fine. These are kind of set to industry standards, so it's fine if you don't touch these. You could actually go in and change the name of some of these, and sometimes, like if someone has a lot of medium sand, they want to break medium sand into sub-grain classes. But the one thing that I do go in here and change pretty often is the unit weight, which somewhere along the line got labeled BD in SI, which I will fix for the next version. But in SI, this is density. In US customary units, it's unit weight. So they're actually not entirely the same thing, but they convert. And so you'll notice that for the sand and gravel and boulder grain classes, our default unit weight is 1489, which is the conversion of the US customary default, but that's about right. If you think, where's the dry density of sand or gravel or something like that, you're going to be in the 1400 to 1600 range. So that's okay. But then look at the silt. Silt's about 1,000, and clay in particular is 480. Now, that's not totally wrong. This is actually based on observations in the 40s and 50s of what the actual density of clay in reservoirs was. And clay in reservoirs, when it deposits, it can be what we call fluffy, which is kind of a funny technical term, which means that early clay deposits have a lot of void space. And so they found that the actual dry density of a lot of deposits in reservoirs can be as low as 500. But that's the low bound. And so as sediment consolidates, then the density increases. And so if you run it with these low densities, your mass will translate into more volume change, which means more depositional distance. And so having no other data, I've found that 1,000 is the low bound that I've interacted with. That's not universally true. I know a lot of folks that work on reservoirs that use 500, but 1,000 is kind of the low bound that I've worked at, and I would probably go with 1,200 here. And again, these are things you would rather measure and or calibrate, but I'm going to kind of bring those lower bounds up to kind of the median range where I've worked at before. Okay, so then we go to options, set cohesive options. Let's leave that for the end. Let's go to bed change options, 1D. And so RAS uses the veneer method, which we call the peanut butter method, which, if we're going to deposit or erode, we're going to evenly spread that deposition or erosion over all of the wet nodes within the movable bed limits. And you can see that for our global bed change options, we basically have for deposition and erosion, what are you going to do in the channel? Well, by default, we're going to use the veneer method for both deposition and erosion in the channel. But you can change these. And by default, on the overbank, outside of the movable bed limits, we're going to do nothing. We're just going to leave it fixed. But I often, and particularly with reservoir models, in the overbank, will select veneer. And so what we're going to do now is we're going to deposit and erode in the channel with the veneer method, but we're also going to allow deposition in the overbanks. And this is important in a reservoir model because the overbanks are always wet. If you think about what is this cross-section going to look like when the water surface elevations are at 260 to 270? Well, it's going to be completely inundated for the whole simulation. And you can see I actually went in and put in ineffective flow areas here. That's pretty important. But that means that if you've got cohesive sediment traveling downstream, this cohesive sediment is going to basically go bank to bank. And so you're going to allow deposition outside of the channel. But then in the parts of the model that are upstream, where the water surface elevation will actually drop so that it is channel flow, then you're not going to erode in the overbanks, but you will erode in the channel. So you want to allow erosion in the channel. And also, if you're going to do some sort of flushing analysis, probably what will happen is that the river will reoccupy its relic channel, especially in the early years. We'll allow erosion and deposition in the channel, but only deposition in the overbanks. And so that's all we'll do here. We're doing this globally. We did add this local ability to do this cross-section by cross-section. I don't love this, and probably in future versions, I'm not sure we're going to have this. Okay, so then we're going to go to options, transport methods. Now this is mostly 2D transport methods. You'll see that this is all 2D stuff down here that you use with the 2D model, but there really is just this one 1D routing method that we use, particularly for reservoir models. And the issue is that we use the Exner equation. And the Exner equation is temporally naive. It doesn't actually track how far sediment can go in a time series. So it'll just move sediment from control volume to control volume without kind of asking, yeah, but what was the residence time of that sediment? And did we give it enough time to deposit? And so, by default, that's what we do. And, it's computationally efficient. But for a reservoir, particularly for silt and clay, what really matters is how long does this sediment stay in there and how much time does it have to deposit. And so we have this option which says limit the sediment to the water velocity. And what that does is in each time step, it looks at how much flow actually leaves the control volume associated with the cross section. And then it says, hey, we're only actually going to let that much sediment go, and we're going to keep the rest of the sediment in that control volume to give it another shot at depositing next time. Now, interestingly, it's still vertically mixed the whole time. And is that the way that sediment works? No, as sediment moves down the reservoir, the center of mass drops, which is another bias, which is another reason why if you kind of think about these gradations, that they often maybe should be coarser than they are in reality because you want to induce a little bit more deposition. But okay, so we went to options, transport methods. We chose limit to water velocity. And so that leads us to our final method, and that is the cohesive options. Now, by default, we use transport functions to move cohesives because we don't want to give you default parameters for this. And the basic gist there is that if you're doing a river model, you could just leave the wash load out of it unless you're looking at concentrations or TMDLs, if you're looking at actual bed change. But if you are doing a river model, your cohesives are generally going to be wash loads. So if you use the transport function, they're wrong. They're going to be wrong by orders of magnitude, but it's still going to move all of the silt and clay. And so that's not a terrible assumption if you're doing a river model. But in a reservoir model that is 90% silt and clay, it's really important to get this right, particularly if you're going to erode. And so we have two different cohesive transport options here. They're both a combination of the Krone and Partheniades models for silt and clay. And Krone is deposition, Partheniades is erosion. But this is one of the things that we did differently than our predecessor model, HEC-RAS. And so there are two different ways to do this. But we're just going to choose the Krone method. And then I'm going to do a whole nother video on what the M form versus the KD form of this is. It's a dimensional and dimensionless form, but let's leave it at M. And the idea here is that below a critical shear stress, you're going to deposit. And above a critical shear stress, you're going to erode. And then kind of above another threshold, you're going to erode at a faster rate. It's what we call the mass wasting zone. And so this is a depositional model. So really what we want to get right is what's the shear stress at which we start to deposit? And this is, again, going to be another calibration factor. We're kind of collecting more than we want at this point, but we're not actually going to worry too much about this. Now, if this was a flushing model, which eventually it will be, then these things become more important, but you would probably want to measure these with a SED flume or a jet test. But what I'm really looking at is zeroing in on this deposition one. Now, the default in US customary is 0.02 pounds per cubic foot, which is 1 Pascal. So let's just start with that. So obviously, the model is going to be sensitive to this, but that's where I'm going to start. What I'm going to do is I'm going to make the mass wasting threshold kind of large. I'm going to make it 10, and then I'm going to put a very low erosion rate in between those so that really we have a zone in which neither erosion or deposition occurs. And it isn't till these high erosion rates that then I'm going to go in and say, well, then we're actually going to get some erosion. But this is all fantasy here. I don't know any of this yet. These are things that I'm going to need to figure out with some data, but in order to get the model to run, basically all I've done here is I have a depositional threshold. Okay, so now I have all the data that I need. I'm going to save it. All right, so now I'm going to run the simulation. So I'm going to go to Run, Quasi Unsteady Analysis Sediment, or I'm going to choose the sediment running person. I'm going to go to File, Save Sediment Plan As, and let's call this 1997 to 2022, 97 to 22. And then I'm going to choose that 01 January 1997 as my start date. And I will end before the data went up to about June 2023, but I'm going to run the 25 years here and say, 31 December 2022 at 2400. All right, so that's great. But before we run, let's go look at the sediment output options. And so you see that we're running at level 3. We're also writing a lot of data we don't need. I'm going to turn off this binary output. And then I want to run at level 4, and I also want to get cross-section output. But what I've noticed is that in the recent version, if I get output every day for 25 years, the profile is actually pretty sluggish in the output. So for now, just to triage it, let's go ahead and kind of get data every month and see the results every month, because we're doing a 25-year analysis. That'll give us plenty to look at for now. All right, so I'll press OK, File, Save, and I'm going to compute. And so that took about 7 minutes to run, which isn't bad, which means we can definitely do better with more cross-sections if we need them, or definitely shorter computation times. But I want to go and actually look at the messages we got. It gives us a write-out of the different methods we're using, and then it gives us warnings and notes. Here it's just saying that, hey, the boundary condition actually had to extrapolate below the lowest flow in the flow load curve, which is fine because it's just going to extrapolate to 0. It's if this comes in red if it actually is over the top of the curve, because that doesn't extrapolate, that just flattens out. And then we have a little bit of a mass budget report, which I find really useful. We added this because I'd really like people to start evaluating their mass budget before they even look at results. And you can get this both either in mass and volume. The difference obviously will be those densities, right? And so depending on how different those densities are, these numbers can be different. But for just looking at mass, because RAS actually works in mass, if we have like 7.8 tons coming in and we've got 2.5 tons going out, well then the trap efficiency, how much of material is trapped? Well, it's this minus this. And so we got about 5.3 million tons trapped. So the trap efficiency is going to be 5.3 over 7.8. So we're looking at like 65 to 70% trap efficiency, which means we're still passing quite a bit of material through this pretty large reservoir. So let's actually go look at some results right now. We're going to go to View, Sediment Output. And let's start with the profile. It does take a little bit of time for the profile to load because the way the HDF5 data are structured, but once you load it once, it should be pretty snappy. We'll go and let's start looking at invert change. If we look at the change in the invert, change, it is pretty jagged, but it also is relatively predictable. I would probably go in and look at these peaky cross sections to see if there's something about my cross-section geometry, usually my ineffective flow area, that's causing that. Then I'm going to turn on the max because the final is not always the max. Sometimes it deposits and then erodes. And so this actually lets you know, you can look at the min too, but the min will be 0 for change. But then what I prefer to look at is actually the cumulative mass bed change. And you'll see that tells a different story, because the mass bed change doesn't just show you what's happening in the channel, it shows what's happening in the whole cross section. And so if you look at a couple of these cross sections, these cross sections are in the 11,000. You can see down at the bottom there. In the next version, we'll actually show you which cross sections these are. And so if we actually go look at those cross sections, I'm going to switch to the cross section plot. And if we look at, say, some of the ones upstream, we'll turn on the first and the final. You can see that's, it's a veneer deposition in a reservoir. That's not outrageous. Especially when you're kind of downstream of any sort of bed low, you don't even actually expect the channel to fill first unless you're getting turbidity currents. But if we go down into the 11s and early 10s where we're getting some of the massive deposition, now we're looking at something weird, right? We have these kind of overbank depressions which are lower than the thalweg itself and are filling with sediment. That's where we're getting those peaks. And you need to ask yourself the question, is that real? And so if we go in and we look at what that cross-section looks like, these cross-sections I drew kind of to include this portion, but this portion is actually a tributary. And so that's actually a channel. And we weren't modeling that specifically, but this channel's lower than this channel. You see this channel actually has built some natural levee walls. And so I think it's a legitimate question as to whether it's appropriate to include that in the model. I might actually truncate these cross sections and try to do something else with that. And so one of the things that I think I want you to get from this is my first run. And so my first run is exploratory. We're nowhere near being ready to answer questions or deliver this model yet. We're going to evaluate the results to see, how is the model performing? Where do the one-dimensional assumptions break down? And, what sort of updates do we need to make to our model in order for this to be strong? Another thing I like to look at is the grain class percent profile. And so that's going to actually show us a gradation in the downstream direction. And so I'm going to look at the cumulative mass change. That's what CUM means, the cumulative mass change. That means the mass change in the bed at all time up to whichever time you select. And we will turn off the first one and then turn on the final one. And what this is going to show us is, the red line is that mass change that we were just looking at. But then it shows us what percentage of the mass change, in this case it's all deposition, is associated with each grain class. And black is clay, gray is silt, and then the browns are the sands. And so you can see kind of as you move downstream, it gets finer because you have more and more clay and less of the coarser silt classes. And you can actually go in and turn on the D50 as well, and it'll show you the gradation dropping in the downstream direction. One other thing I like to look at, let's go back to the profile. And at this level, output level, I'm only doing the mass into each control volume. I'm not defining the mass out, but that's a good enough surrogate. And so what we can do is we can look at the mass flux into each control volume at any time step. And this is cumulative, so it's over the course of the whole simulation if you choose the last time step. So this is the mass flux that comes into each cross section for the whole model run for all 25 years. And so you can see as the purple is the total. And so this is the mass that's coming into the upstream cross-section, but we don't have any other sources or sinks other than deposition in the model. And so this is the mass that's leaving the whole model, or at least minus the downstream cross-section. And so that is actually your trap efficiency. That shows you everything between those two numbers is deposition. And this number and this number divided by this number will give you the trap efficiency. But then the thing I like about this plot is then it breaks down by grain class. And you can see these darker grays are the coarser silt grain classes. And you can see that they all go to 0, which means that they all have 100% trap efficiency. All of the coarser grain classes basically go to 0, which means they're completely deposited within the reservoir. But the finest silt and clay don't go to 0, which means that they're actually passing flux through the reservoir. They don't have 100% trap efficiency. And so if you need more trap efficiency, if you feel like you're passing too much sediment, if you're getting, let's say you have downstream concentration observations that are in your results are too high, then you can move material from your fine silt and clay grain classes and assume, oh, actually there's more flocculation going on than I thought, or the vertical mixing bias is stronger than I thought, and you can move those into the coarser grain classes. And so that's just a very kind of brief primer on a very simple reservoir model. To wrap up, let's actually look at the reservoir profile. If we go in and we say, hey, I want the water surface in profile, and I want the bed elevation in profile, and we're going to turn on the front, the first and the last, you'll see kind of what our deposition profile looks like. But you'll notice that our high water surface actually daylights at the top end of the model. This is not ideal because reservoirs do tend to build deltas kind of upstream of where the water surface daylights. And so this is actually just all of the geometry I had. But one of the things that I'd want to do to make this model better is actually extend this geometry, I would say another 5 kilometers upstream, so we could get the coarse delta that builds in that part. One of the reasons why putting coarse material into this model doesn't really work is because the coarse delta often develops upstream of that where that water surface daylights, and we don't really have capacity for that in our model. And so that's a my first shot at a very simple model of the system, but I did think that it provided some lessons learned along the way, that if you're building a reservoir model, that it would give you some insight on where people often make mistakes and some of the options and methods that are most useful for reservoir modeling. My name is Stanford Gibson. I'm the Sediment Transport Specialist on the HEC-RAS team, and this video was funded by the HH&C SET program.